right? So this says if a function converges to a limit, in other words, if we write something like this, lim as x goes to x naught, f of x equals L. If that's true, then every sequence that converges to x naught drags f with it, so that f of x n converges to L, right? Drags it along. So that should be clear. Okay. How about the other way? So now we would like to show, this is the more interesting way. This says the convergence implies sequential convergence. Now we'd like to show sequential convergence implies convergence. You write this down. Sequential convergence implies convergence. All right. We can prove that directly, or we could do what?
Indirect.
Yeah. Well, the contrapositive and the statement are true at the same time, right? So we proved converse. Now, if we say if it is not convergent, then it is not sequentially convergent. That, okay, the contrapositive.
Not sequentially convergent.
Here's a statement we'd like to show. A implies B. So not B implies not A is the contrapositive, right?
Right. So not sequentially convergent implies not.
Or not convergent.
No, this is the other direction.
Oh, you want to? I thought you were talking about that.
No, I thought we proved that. Or
Yes.
You're not accepting
No,
that?
I like it.
You like it? Okay. I think we can let that one rest. We have proved that convergence implies sequential convergence. We'd now like to prove the converse, that sequential convergence implies convergence. So what if we just try the contrapositive? So if we don't have convergence, that means that means what? That no matter how close you get, you can always find somebody that jumps away from the limit, right? Closed limit. Does that imply that you don't have sequential convergence? Okay. Assume F does not converge to L. Want to show there exists a sequence that does not converge to there's a sequence such that f of xn, corresponding sequence, does not converge. Isn't that going to do it? Isn't that the contrapositive of the original statement? We want to show sequential implies convergence, so if we turn that around, not convergent implies not sequentially convergent. That will do it. Right? Nobody looks too confident about this. Logically, it's all right, though.
So the XL will converge to X naught?
Well,
But after that, something
the x's will march in, and then this thing will go through Kerfluid. Okay? So if F doesn't converge to L, that means, if we fix epsilon, there exists a delta of epsilon such that we're close. But f of x minus f of x naught. Oh, sorry, this is L. I keep saying this. L is greater than or equal. The negation of less than epsilon is greater than or equal to epsilon. Okay. All right, can we? Well, I can get within delta of x naught. Let me pick an x1 that's within delta of x naught. Okay? So I'm going to use this condition to find an x1 that makes that true. However, f of x1 minus L is greater than epsilon, even though x1 minus x naught is less than the delta. Right? So I'm close here in the x's, but for some reason I'm being pushed away from the limit over here because the original thing doesn't converge. I'm allowed to go find that, right? In other words, I can still be close in x's, but far away, relatively, in corresponding function value, right? Okay. Having put down x1, I can find an x2 that is, I can find an x2 that's even closer count. I can pick epsilon over 2 as an x. And right? And because it's not convergent for that epsilon over 2, I would find an x2 that is within delta of epsilon over 2, right? Such that I still have more than epsilon over, I'm still more than epsilon over 2 away. I want to cut that epsilon in half, though, do I? I want to keep everything away from it. I want to get closer in x. Yeah, I can do that. I can do that. I have x1. There's uncountably many points between, in the interval x naught minus delta, x naught plus delta. And I'm picking one out, x1. Put him on the shelf. Now I would like to go back and find an x2 at is half of delta away at max, but still this condition holds. Then I'll like to find an x3 that's a third of delta away, but this condition still holds. Okay, so I continue that, and I get x1, x2, x3, x4, blah, 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 right? Would you say that they would be convergent to x naught? By choice, I trim delta down each time, right? And then first delta, and then I get closer and closer and closer and closer. X ends are marching in and x naught. But in every stage of the game, f of xn is no closer than epsilon from L, right? You believe that? Because f doesn't converge, I can always do that. There's always some rogue value that I can pick that puts me at least greater than or equal to epsilon away, even though I'm within some tolerance around x naught. So I've constructed a sequence that doesn't get within epsilon of the sequence converges to x naught, but the values of the function evaluated at the sequence numbers never get to within epsilon of L. So that sequence of function values doesn't converge. The sequence converges, but the function values on the sequence don't converge. They're always stuck at least epsilon away from L. Okay? Does this make any sense? That's saying isn't it?